Okay, I wanted to shoot a quick video to go over section 5.3 from the My Math Lab homework because it has us solving a few equations. And I know that the Moodle lesson tends to emphasize how to solve things graphically, and that makes this stuff with logarithms kind of optional. But I wanted to go ahead and have you practice how to solve these things algebraically, because some of you will go on to a chemistry class or some other class that requires you to know how to use logarithms to solve an exponential equation, and you won't have the graphing tools necessarily like Desmos. So this is one of the reasons why we present logarithms in this course, is so that we can use them when we have to algebraically calculate an exact answer for the solution. So before I went into, I'm just going to work through the homework problems and show you, explain how I would do them with algebra. And of course, you can verify them graphically. But before I did that, I wanted to just quickly, I hope everything's quickly. I will go over, where's my ink pen? The basic properties that I want us to kind of be focusing on. So I can get this more lined up. And one of them is just converting back and forth between the algebra, the exponential versus the logarithmic equations. Okay, so if you have a base, I know in the Moodle it has words to explain this. I'm just going to go over it really briefly. We have a base number. We raise it to an exponent value, and out comes the answer. So like 5 squared equals 25, something like that. Okay, we already know we could rearrange these things to talk about square roots of this number equals that number, but also there's logarithms that are another way to express a relationship between these three. Since we call the base under an exponent the base, every logarithm must also have a base attached to it, and it's referencing the base when it's in this form. So log base b is referring to this type of base, and we switch these around. We're taking the logarithm of the answer, and it's going to calculate the exponent on this base when it's in this form. So if we had 2 to the third power equals 8, we could use logarithms to say the log base 2, get the base right, of 8 equals, this is calculating the exponent that we need on 2 to change it to 8. And the exponent would be 3. So logarithms just calculate exponents. Okay, so this is the logarithm right there in this form. So that's why we have logarithm of blah, blah, blah equals, this is referring to an exponent on 2 that changes it to 8. Okay, so we had a couple of special logarithm bases. There was one that if we don't write any base at all, that's considered to be log 10 or base 10. Okay, so we call that the common, sorry, gotta get my words right, the common log. And if we worked in base E a lot, because some of those financial applications, when we compute things continuously, compound interest continually was base E. So we use ln of x, and that means the natural log. And so that would be the same thing as working in base E. Okay, so they also undo one another. So if I ever have 10 as a base and I need to get rid of the 10, I can apply a common log and it will get rid of it. If I have a base E, like in my compound interest formula, so I'm working in base E, I might apply a natural log to that expression, and that would eliminate the E. All right. The other thing that we want to be able to remember how to do is the power rule for logarithms. So remember, if you have a logarithm, whatever base you're working in, and let's say you have something else inside your logarithm and the bases don't match necessarily, you can still use what's called a power rule. And I know that in the Moodle lesson for 5.2, there was a big explanation about why this is true, but it is true. It goes back to all those rules for exponents that says it's equivalent to take what was in the exponent and write it in front of that logarithm as a multiplier. And we use that quite a bit when we're trying to solve equations. All right, so we have the power rule for logs that we're going to use. And this isn't even the only way that you can do these algebraically, but this is the way the chemistry people like it. So I'm going to use this one. So when we're trying to solve exponentials, I'll apply a logarithm and then use that logarithm form to bring the exponent out in front so that it is no longer an exponent. But sometimes it's even more simple. We'll just convert an equation from one version to another, particularly when we're working with the logarithm types of rules. We can get to this point and just convert it over to an exponential, and we can see the solutions really quickly. All right, so let's just run through some of the homework problems. Just in the interest of time, I printed them all off. That these are the 8 problems that are in 5.3. Let me see if I can zoom in here a little bit more so we can see them up close. Focused in, nice, right that there. Okay, so on the very first one, we are solving where the x is up in the exponent and the base is e, and it just solve it. It says back check it graphically, so that's where we could go to Desmos, but I won't do that part today because that part is explained pretty well in Moodle. All right, so if you're trying to solve an expression and the x or whatever it is you're solving for is in an exponent, well, that exponent has to be attached to a base. And that little piece right there, the base and exponent together, I want to make sure that if you're solving these kinds of equations that you isolate that piece right there. So if there's any other number multiplied out in front of your base or added as an extra term out here, we want to eliminate those numbers and then work on using logarithms to finish it up. In this case, the base is already just base e. So what we're going to do is, this is the step where we will apply a logarithm to both sides. Okay, so if you get your base and exponent isolated, the next step is to apply a logarithm. Now, you can use the common logarithm or you can use the natural logarithm. But I'm going to do the natural logarithm, in this case particularly because it's base e. I might use natural log all the time just out of habit. Chemistry people, at least a guy I talked to did the common log every time. Anyway, so the first thing we're going to do is we're going to apply or take a natural log of both sides of this expression. So we'll do natural log of whatever is on the left equals the natural log of whatever is on the right, like that. So when you apply a natural logarithm, you write it in front of what you're working with. Okay, it makes no sense just to write one like this without anything after it. Okay, so you have to apply it to something that follows the logarithm symbols. Okay, so this is just a weird number. Remember we said logarithms are just exponents? So I could put this into my calculator. Everybody's scientific calculator has the LN button, and we could get whatever weird number that is. But what we want to do is get this form on this side. So the side that had the exponential piece to it with the x up in the exponent, this is what we're going to do. We're going to use that power rule to rewrite the right-hand side by moving everything in the exponent out in front of that logarithm. Now I'm just going to copy the other side straight down. I'm not making any adjustments over here, but I'm going to take that 3 times x and bring it out in front of, oh, I guess I could even do this faster. Natural log of e, those two things actually cancel. So I could do that even faster. So either bring the 3x out in front and the natural log of e becomes 1, or you could do it in one step and say natural log and e, because those actually do deal in the same base. They actually just cancel out. So we'll just get 3 times x on the right-hand side for whatever reasons equals this natural log over here. So then just ask yourself, well, if it's 3 times x and I'm trying to solve for x, what do I do there? I just divide by 3. So even though the left-hand side has got this funky logarithm in it, which is now the right-hand side, I'm going to flip it around. That's just something I could put in my calculator if I needed to get a decimal estimate, and then I want to divide the whole thing by 3. All right, so this is my exact answer. If it asks for the exact answer in the homework, it needs the logarithm piece in it. And logarithms are kind of like square roots that if you put them in your calculator, you'll get like an indefinite number of an unending number of decimal places that you have to round off to whatever you need. So don't round it off right here at the beginning and then do further calculations, because every time you use a rounded value in a new calculation, you get less and less accurate. So make sure you don't do any evaluations on your calculator with logarithms in particular until you get down to the final step. So this is the exact answer. If I needed a decimal estimate, I could go to Desmos or another calculator and do natural log of 8936, make sure you close the parentheses, and then divide that answer by 3, and that gives us x. So whatever it is in the calculator, notice it does say round to 3 decimal places. So whatever it is, I would round it off, but I'm going to move on to the next one. All right, so number 2. This one is just making sure that you know how to evaluate something with a funky base on it that's not one of the 2 that's in our calculators. Everybody has the base 10 and the base e logarithms on their calculators, but we don't necessarily have a base 2 feature on our calculators. Some calculators do, but most don't. So the change of base formula just means whatever logarithm you would like to work with, I'll pick common log this time, just because it's on everybody's calculator. You make a fraction. The change of base formula was also explained in the Moodle lesson. You just do, in the numerator, it's just taking a different type of log, like a common log, of whatever you were doing anyway, which was square root of 10. And then the denominator is the same kind of logarithm, common log of whatever your old base was. Okay? So the change in base formula is pick a log that you want to do on your calculator. You could also do this with natural log. I could do natural log of whatever was already there, and the natural log of the old base. Okay, I am going to switch over to Desmos really briefly here to show you that, to prove to you that those really do match. So let me go to share screen. Let me go. What would it be here? I think. Let me see if it's in there. I thought I had Desmos. Let's do Desmos, and then I'll share that one again. So Desmos. Go to Desmos. I'm going to stop and start the share again because sometimes it doesn't transfer when I switch my windows. All right, so there it is. If I wanted to do that, what I just said before with the common log, I could just do log common log of, and then I'd want to put square root of 10 in here. And we have a template down here. So square root's right there. Square root of 10. Those are my parentheses. And then I'm going to divide this by same kind of log, common log, and then of my old base that I was given. So I was given that base of 2. So that's equivalent to log base 2 of the square root of 10. So the change of base formula is pick whatever log you want to work in. I'm going to do the same thing just to prove to you, doesn't matter which base. I'll do common or natural log, and then we'll do same thing, square root of 10. Nope. Square root of 10 divided by natural log of 2. Whoop, I didn't do the divide by. Let me get back up in there. Divided by, there we go, natural log of 2. Okay, see how it gives us the same decimal estimate? That's just like 2 different kinds of fractions that reduce to the same thing, basically. So as long as you work in the same type of logarithm in the numerator as you do in the denominator, you can take any weird base, like my number 2 said log base 2 of square root of 10. Pick your favorite log button, do the regular input on the numerator, so common log or natural log of square root of 10, because that's what was in my original problem, and always divide it by that same type of logarithm of the old base that you were given. So mine was given log base 2 of square root of 10. All right, so anyway, that's probably all you're going to see of Desmos, but I just wanted to show you that that change of base formula really does work on regardless of whatever base you're working in. So what was it, 1.66 something? I don't remember. All right, you all will get different numbers, as you know, when you work through this anyway. All right, so let's look at number 3. So this one, the x that we're solving for is inside of a logarithm. So I like to use parentheses here, but my math lab often doesn't do that. But log base 4 of x equals 2. So when you're solving for a logarithm where the variable is inside the logarithm, like here, and look at number 4, the x that we're solving for is inside this natural logarithm. What you want to do, kind of like what I said earlier with the exponential pieces, get that logarithm by itself. Make sure that's the only thing on that side of the equation. And then we're going to just things you could, a couple of choices, but I'm going to go with convert it over to its exponential equivalent. Now this one doesn't have any multipliers out in front, so it's good to go ahead and convert. So I'm going to convert over to its exponential equation, which I had just done that on the intro sheet. So my base is going to be 4. The exponent is what the logarithm is equal to. So this is the exponent on 4, so 2. And then we write equals whatever we were doing was the input to the logarithm. Okay, so this is the exponential equivalent. The base of 4 raised to the exponent of 2 is equal to the x. Then we just take a fresh look at this new version of the equation and say, well, how do I solve that for x? And you say, well, x is already solved for. It's by itself. I just need to compute 4 squared. So in this case, x is 16. I don't have to really do anything. Just simplify 4 squared. I didn't have to move anything else around. If this had said 5x, then I would divide by 5 or something. But all I really had to do was just compute that 4 squared. So really all you had to do on this one, convert it to its exponential equivalent, and it pretty much solves itself. Okay, let's look at number 4. It's similar, but it's got a little couple extra steps here. I have the natural log of x, but I also have a 2 and a 4 that are not part of that logarithm. So I need to first move those 2 numbers to the other side of the equation using our rules for solving. And just like any solving, you start from the number on the outside and work your way in. So we're going to subtract 2 from both sides first. So minus 2, minus 2. So I'll have 4 times the natural log of x equals 10 minus 2, 8. Okay, then I still want to get the natural log of x isolated. So now I want to work on getting this 4 removed. And since it's 4 times whatever, we're going to divide both sides by 4. So now we get just the natural log of x equals 8. Okay, so now we have our logarithm isolated, just like we did at the very beginning of this one. So at this point, I would like to convert it over to an exponential equation. So to do that, I have to figure out what my base is because there's nothing written, but 8 is going to be the exponent and it's going to equal this x. All right, so down here, the base on natural log when nothing is showing is e, remember? So my base is e, even though it's not written. The exponent is going to be whatever that is equal to the logarithm. So e to the 8th equals whatever is in the logarithm, which is just x. So again, this one is already solved. So e to the 8th would be your exact answer. If I needed to work that out on my calculator, remember E is at 2.7218 something something, a number that goes on forever. You would put all this into your calculator and then estimate it to whatever. But this says use an exact answer. And it's giving you a hint that you're working in base E. So just type in mine, I would just type in e to the 8th, and that would be the exact value. Okay, so let's look at number 5. Number 5, we're going to solve it algebraically again. Now we're back to where our x is an exponent on the base of e. So I would like to get the e and the 9x by itself because that's my base and exponent piece. The 3 is not part of that. So the first thing we're going to do is divide that 3 to both sides because it's 3 times e to the 9x. So I need to undo times by dividing. Okay, so I'm going to do e to the 9x equals 477 divided by 3. I'm not going to try to do that in my head. I probably should. But 477 divided by 3 is 159. Okay. That time it was okay to use my calculator to do 477 divided by 3 because it came out evenly, 159. But if I tried to do this and it was divided by 7, it was some kind of funky doodle answer that goes on with decimals that just go on forever. Don't write a decimal estimate here. Go ahead and just write the fraction and then let your calculator compute all of it at once at the end. Don't round too early. Okay, so we have now isolated our base with our exponent, and the x is up in the exponent. This is where I apply a logarithm to both sides. When you have your base and your exponent isolated, apply a logarithm to both sides. I'm just going to almost always use natural log unless I'm specifically working in base 10. I'm always going to use natural log because we do have that continuous compound interest that works in base e. So when you apply natural log to e, they cancel out. So it saves us a little step here. Natural log of 159. Okay, so when we do this, I could move the 9x out in front with the power rule, but actually this is a faster formula because natural log and e are inverse functions of each other. So they cancel out directly. And all I have left to do to finish this is do that logarithm, divide it by 9. So I'm just copying down the right-hand side. I'm just simplifying over here. Now I've just got 9x. Instead of 9x being in the exponent, everything else canceled out. So that old exponent is now the only thing that's left on this expression. So now I'm going to divide both sides by 9, and that's my exact value. It says round it to the nearest thousandth. So that's 3 decimal places. So at this point, you could put that into your calculator to get your estimate. Okay, so that's you put in your calculator to estimate. Okay, but get your base and your exponent isolated, then apply a logarithm to both sides, and then either use the power rule to bring this stuff out in front and then divide away what's left, or in this case, because it's base e, we can actually use a shortcut and use natural log to cancel out the e directly, and that just makes it solve a little faster. Okay, let's look at number 6. Number 6 is base 10. So I think when I get to the point where I do the log on both sides, I'm going to pick the LOG button this time because that will cancel out the 10 directly. But anyway, first thing we need to do is get that base and the exponent by themselves. So I need to get rid of the 500 because it's not part of the base and the exponent. So I'm going to divide both sides by 500. Okay, so this happens a lot in those financial applications. I think that's going to be, I don't know, 5 or 50, something like that. 112,500. 500 divided by 500. I don't trust my brain to do this, so it's 25. So when I divide this side, that's going to be 25 equals 10 to the x. Again, I was able to use my calculator here because it came out exactly 25. I wouldn't want to use my calculator if I had to something I end up having to round off. Okay, so now I have just 10 to the x. I would like to basically get rid of the 10 somehow and keep the x, so I'm going to apply a logarithm to both sides. This time, because I'm working in base 10, I'm going to use the log to both sides. So I'm going to do common log, which is base 10 logarithm of 25. Just write it in front of whatever you're doing it to. It would be the common log of 10 to the x. Okay, so just like base e and natural log are inverse functions and they cancel out, base 10 and common log, which has sort of an invisible assumed base of 10, they also cancel out. So that means this case is actually solved. The x up in the exponent, that's all there is. X equals this, common log of 25. Okay, so that's my exact answer. And again, if I need a calculator, see, I'm working in a base that I can go right to any of my calculators. I can do it on my phone, or any calculator that has a log button will have this common log button. So just common log of 25, rounded off to 3 decimal places, goes right there. Okay, let's look at number 7. Number 7 has got some stuff going on because the x is up in the exponent, which means we're going to use logarithms at some point. I don't know if you can hear my puppy barking, but my husband can deal with that. All right, so there is our equation we're trying to solve. The x is up in the exponent. In fact, there's a whole big thing in the exponent here. All right, so the rule is, if I have an exponent, there must be a base to that exponent, which is 4. If there's anything else other than the base and the exponent, I need to move it around, like we had the 500, and I need to move it away. I don't have anything else but the base and the exponent. So I can start right away with applying a logarithm. So I'm going to apply, I don't care, my favorite is natural log, so I'll do natural log. 4 negative x plus 2 equals natural log 93. Now this is where we'll get to see the power rule come in play. All right, so I did this. There was, rather than try to match a logarithm with the same base of 4 and then have to use a change of base formula and stuff later on, I'm just going to always use natural log when I get to this step. Okay, so it won't cancel it out, but what it does allow me to do is take that exponent and to move it out in front as a multiplier. All right, so negative x plus 2 will become a multiplier. Now, all of that is getting multiplied. Make sure I use parentheses to be careful here. Natural log of 4. So the entire exponent becomes a multiplier against the logarithm of whatever's left, that base part. And I just copy down the right-hand side. I'm not really making any adjustments over here. All right, so now let's look and see what I've got. I don't have, the x isn't in an exponent anymore, so it means I should be able to figure out how to get the x by itself. Typically, if this weren't such a funky looking number, a lot of times people will distribute to get rid of the parentheses and all that. I'm just going to divide the natural log of 4 under this side. That's another way to get rid of it. The parentheses are only there to indicate all of this is getting multiplied by that logarithm. So if I just divide that logarithm, then it's gone. I don't need the parentheses anymore. Negative x plus 2 equals, and I had natural log of 93 there, and I'm dividing both sides by that natural log of 4. So natural log of 4. So here's where I'm at now. Oops, put that all the way down here. All right, so all I have to do to finish this up is just look at this side, ignore this over here. I know it's funky looking, but I can get all that into my calculator. Just take this and say, all right, to get the x by itself, I need to minus the 2 and then divide everything by negative 1 or change the sign on everything. And that will be how I solve for x. So I'm going to minus 2 from both sides here. So that'll leave me negative x on one side. I'll minus the 2. This is some funky number I'm not prepared to deal with yet. So I'm going to just leave it as a fraction and slap the minus 2 on the outside of it. If I'm going to do a decimal estimate, that's what I would do first, is I would do this logarithm divided by the second logarithm on whatever decimal answer that is. Then I would subtract 2 from that. And then the very last thing I would do would be to change its sign, because I have to change the signs on both sides here. All right, so to finish this up, I would divide everything by negative 1 to change the sign on my x. So positive x would be, I could put a negative in front of all this, or I could just switch these two things around. Right now, the fraction is positive and the 2 is negative. So one way, if I'm going to divide everything by -1, I could just switch that around. Uh-huh. 4. All right, so that would be one version of the exact answer for that question, because now it's solved for x. So this has a little bit more to it. Typically, when we do solve one of these exponential equations, it does have something with 2 logarithms being divided like that. And then, there may be something else you divide by or add or subtract from like that. So that's the exact answer. And if I needed to do the decimal estimates, we could do, like I said before, we could do 2 minus and then, or do this part separately and then subtract it from 2 or whatever you want to do to get the decimal estimate for that. All right, so the last problem I had already done previously. I'm sorry this is so long. Let me go ahead and talk. I'll just talk you through this one because this one doesn't really require any solving. I just wanted to make sure everybody kind of knew what the reasoning is. So this was based on some old Super Bowl data, I think, for how much it used to cost to advertise during the Super Bowl and how expensive it's gotten, in the last 20 years or so. So back in 1973, the cost for a 30-second ad or for a 1-minute ad was $200,000. But now we're in the 2000s, and in 2004, it cost $3 million for a 30-second ad slot. And so someone has taken some of that data over the several years, done a regression, and they came up with this model, the 0.000962 times 1.105 to the x. When something grows that fast, it typically is some kind of exponential type of behavior, where x is measuring years after 1900. Okay, so this would have been x equals 73 right here. 2004 campaign, well, that's over a century after 1900. So 2004 year would correspond to an x value of 104 plugged into this. And then notice that the outputs are in $1 million. Okay, so that's the first thing I noticed on this is when it asks us to just plug in a number basically and get out the answer, make sure you convert it to millions because it doesn't have $1 million blank here. It just says $sign. So it says round to the nearest dollar. So what you would do for this one, 2005, well, that's a year after this one. 2005 is 104 years after 1900. Just subtract your start year. So you need to put in 105. Did I say 104? Plug in 105 right up here and just work it out on your calculator. And what you will get will be 3.437275, blah, blah, blah. Okay, so if you take 105 and plug it in there, this is what you should get out with the decimal after the 3.434275 or something that rounds to 5. But it asks us to actually convert it to dollars. So the 3.4 is in million. So I would need to take that number and move the decimal 6 times to get it into actual dollars, or basically multiply it by 1 million. And you'll have to round that very last digit. Okay, so what comes out of the function is 3.437275, but we have to convert it to dollars because it's measured in millions of dollars. So we have to take that decimal, times it by 1 million, and that's where we get that big number there. Okay, then they ask us for different years. So they tell us, so the cost of a 30-second ad in 2015 was $6 million. Does the model overestimate or underestimate? So the model is always the formula that we got based on past data. So if we were to take now 2015 would be 115 years after the 1900. So we'll plug in 115 for the x right there. So again on your calculator, 0.000962 times 1.105 to the exponent 115, and we work out what the answer is. Now, it turned out it was way high. When you plug in 115 here, you get 9.329 something or other. Okay, so it definitely overestimated. This is an answer already been filled in. Okay, so you'll have to choose between over and underestimate. Kind of depends on what you get. But I compared my 9.3 to the 6.0 million and realized it really overestimated by the time we were at 2015. So this is what you would plug in. It just says, what did the model estimate for that year? Again, take your 9.329 blah, blah, blah that came out from plugging it into this and make sure you multiply it by 1 million. So you'll have to move your decimal 6 times and round that final decimal place. So $9,329,042. All right, so that's just a quick talk through how to do the algebraic things. I know it wasn't all that quick. I'm coming in at right about 30 minutes, I think. But let me go ahead and get this up so you guys can have some additional resources while you're working on that homework set. Okay.